Show. Recording. Keyboard working. Nope, naturally. Now it is. Okay, great. All right, welcome back to 152, 252A. We're going to continue where we left off, talking about pipelining. We'll get into some more advanced pipelining for some more advanced microarchitectures today. I don't have a slide on announcements, but there will be either as of right now or sometime today, a large announcement posted to the Ed discussion, and a copy verbatim of it will also be posted to the course website, detailing just a bunch of logistics that have been resolved. So it's kind of like a laundry list. I'm not going to go through it in class. I don't think it's quite public yet, but look through it. It will resolve things like discussion section time for 252A. It will re-articulate homework deadlines, lab deadlines, wait lists, things like this. And if there's any concerns with it, feel free to just email us or post to Ed. Without further ado, though, let's get on with the technical material. So we ended last time, let me get through this slide, talking about how for certain control flow instructions, you will inevitably have to introduce bubbles into your pipeline immediately after the control flow instruction. For example, a jump instruction, which is not resolved as a jump until the decode stage. And so one way that early ISAs sought to deal with this was with this concept called delay slots, where you have at the ISA level a contract stating that the instruction after the branch in the program binary will be executed and counted as an instruction that gets executed in program order immediately before the branch. So the only restriction on this is that it cannot be an instruction which updates something about either the branch's target or condition. This is nice because if the compiler or programmer can figure out something to do in that delay slot, we avoid the bubble. It's not nice because it introduces something at the ISA level that reflects on the microarchitecture, where the whole point of the ISA is to be as microarchitectural agnostic as possible. And for that reason, this idea kind of got phased out over time. So it encodes a microarchitectural detail. This is not very clean. It can actually result in performance issues if you can't figure out what to do with your NOPs immediately after branches, then your code memory bloats. If your code memory bloats, you need more iCache for a given program size, which means that your either iCache access latency, just because of the amount of iCache that you need, is going to increase because the iCache has to get larger, or you're going to, for a smaller iCache, suffer more cache misses on average, which again leads to a longer average memory access time. It also complicates life for more advanced microarchitectures. Imagine you have, this is I think where we ended lecture last Thursday, a microarchitecture that fetches multiple, let's say 4 to 8, this being realistic for today's machines, branches or instructions per cycle, 25% of which are branches, each of those branches having delay slots and having a non-zero probability of there having to be a second branch in the delay slot, which is also something that is typically disallowed because it will make your hair catch on fire if you try to design a microarchitecture with branches in the delay slots. Suffice to say, for more advanced microarchitectures beyond those that the delay slot was originally introduced to simplify, things get quite hairy. Not to mention it, like in parallel to all of this, microarchitectural advances such as branch prediction were enabling us to resolve the direction of branches or jumps earlier, negating the whole reason for having these ISA level, ISA visible delay slots in the first place. Okay, so that's delay slots. We will come back to them when we look at more complex pipelines and see how hairy implementing an ISA with them would actually be. But for now, let's finish the story. So from last lecture, just to kind of go back and reorient everyone. Oops, did I go a little bit too far? Bloop, 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 bloop. Data hazards. Way too far, wow. Control hazards. There's a number of instruction types that we have to walk through in order to understand when different pieces of information needed for them to execute becomes available so that we can understand what the potential performance penalty and microarchitectural strategies for dealing with them efficiently would be. So we went through unconditional jumps. We're about to do jump register and conditional branches. The key feature of these being that they require information that is not typically known until even later in the pipeline. So for unconditional jumps, recall from last time, we have the PC of the jump because it comes with the instruction as it's fetched. We have the direction because it's always taken. We have the offset because it's PC relative, and the offset itself is given to us in the jump instruction. Life is slightly more complicated for jump register, which jumps to a value held in a register, and a conditional branch, which conditionally jumps based on the value of a predicate to a PC relative offset. So let's see how that works. Finally, back to the slide I want. So this is just the equivalent slide that we showed earlier for jump instructions, but for control instructions, illustrating what information we need to resolve a conditional branch, when that information is available, and at a high level, the control signals that are needed to redirect the pipeline when we resolve this information. So for a branch, there's two things that we need, or several actually, three things that we need. We need to know if it's a branch. This becomes available in decode like with every other instruction. We need to know what the condition of the branch is, whether it's a taken branch or a not taken branch. And there's one more thing that we have to know, which isn't shown explicitly in red on the slide, which is what the branch target location is. But if you look carefully, you see a separate add unit that has been added to the decode stage of the pipeline, which uses the branch offset and the PC derived from the branch PC to determine what the target is. And that information goes back, and similar to the way that we handled jumps before, a control signal indicates that this will be our next PC, as opposed to the original PC. So there's nothing fundamental about this diagram in terms of the microarchitectural elements that we've used to implement branches. We could have implemented a pipeline where we only had one add unit, just like we discussed with the bus-based data path from earlier. Having a separate add unit to calculate the target is not fundamental. But if we had that alternative implementation, then we would not have been able to calculate the target until later in the pipeline. We would have to use the execute stage. And sadly, we're already using the execute stage for something related to the branch, namely calculating the condition. In many ISAs, calculating the condition is implemented via basic arithmetic operations. Like if you want to compute whether one value is greater than another, you can subtract one from the other and then use a two's complement encoding to determine whether the result is negative. So you can actually use the same type of arithmetic for both the condition and the target control. So that would complicate the pipeline in two respects. A, you would not know the target until later, and B, you'd have a structural hazard in the execute stage where you have to sequence through both of these arithmetic operations using the same add unit. And so it's very common in a pipeline like this to go the other way and to just bake in a separate add unit, because by this time registers are getting cheaper, logic is getting cheaper, and this just kind of straightens out the pipeline. Okay, so pipelining for conditional branches. Given that we don't know the condition until the execute stage. So going back to the pipeline diagram style from last time, and the thing to really be careful of here, and the thing to really be careful of with any type of pipeline waterfall table where the columns of the table are cycles that indicate when an instruction is in a particular stage, and the rows indicate what instruction we're talking about. The thing to be very careful about with these tables is to, for however their notation goes, avoid off by 1 errors, because that will, usually the question's asking something like, okay, for a particular instruction mix, what's the number of bubbles that you expect in the pipeline? So just when you see this either in discussion or p-sets, be careful to kind of orient yourself around the notation and try to avoid these off by 1s. With a branch, kind of intuitively, given what we saw with a jump, where the jump information is resolved in the decode stage and leads to a 1-cycle bubble, the branch, since we're resolving information in the execute stage, namely whether we take the branch, will result in a 2-cycle bubble. So we resolve the direction of the branch by the end of the execute stage. And just to say, for argument's sake, if we decide to take the branch, we have to flush or insert a bubble, enable the appropriate kill signals into the pipeline to indicate that the instructions fetched in the shadow of the branch should be not allowed to write back. And then finally, we allow the target, we fetch the target at the end of the execute stage. So note the forward causality here, where we don't actually fetch the target until we know that the condition is true, which is intuitive. You wouldn't want to fetch the target unless you know you're going to take the branch, at least in this pipeline where we don't have prediction. So you have to insert 2 bubbles, and then you have a target. And kind of going back to this notation from last lecture, the way that we insert these bubbles is through these kill signals, where the fkill signal means that for the instruction that is going to be latched in the registers at the end of the fetch stage, that instruction as it travels through the pipeline will not eventually update architectural state, just based on us flipping this kill bit where F stands for fetch, fkill. And then we have the exact same thing in the next stage. For the instruction that was in the decode stage, we'll just flip this bit from the control logic to indicate that, yep, we read values out of the register file for this instruction. It's ready to go in the execute stage, but the operation that it's going to do is not eventually going to update architectural state. So this is conditional branches. Any questions? Okie dokie. Jump register. It's exactly the same. Despite the fact that jump register is a bit simpler, it's an unconditional branch that jumps to the value in a register that we read from either the register file or a bypass path. It still has the same type of stall or interlocking bubble characteristics because we don't have the value of that register until the end of the execute stage. All right, so now we've gone through different types of hazards, mechanisms for alleviating those hazards, interlocking or kind of stalling, bypassing, speculation. I want to kind of go through why, even with all of these tricks, we might not be able to get an instruction dispatched, which is to say, doing useful work that will eventually update architectural state in each cycle of the 5-stage pipeline. So the first reason is kind of intuitive if you're dealing with an area budget. The bypassing trick that we went over in the last lecture is not a silver bullet, and you need to add more wires, kind of looping back into the execute stage, build larger muxes. This will have the effect of possibly slowing down your critical path because you're adding more logic to the execute stage, and it will increase the area cost of the execute stage. Now, even if you have full bypassing, does anybody see a sequence of instructions that will still lead to stalls or interlocks on the pipeline as we've described it so far? Let's not consider control hazards. So just take arithmetic, memory instructions, and in terms of data hazards, let's say I fully bypass the pipeline. Is there a sequence of instructions that is going to cause the pipeline to stall? Does anybody have an idea? Can anyone come up with a sequence made up of only arithmetic instructions that will resolve and install? Yeah. Exactly. Exactly. I'm not going to try to scroll back to the pipeline diagram to show how this breaks the laws of physics, but I encourage everybody, if you're having trouble seeing it, to work it offline. If you have a load which writes to a register, let's say X1, and then the instruction after the load is, say, an arithmetic instruction that uses X1, like X1 plus X2, or the contents of the register file at X1 plus contents at X2, you will, despite having completely bypassed this pipeline to the extent that you can, be forced to stall. And that is because the subsequent instruction, the add, which depends on the load, is already going to be in the execute stage and need the result of the load before the load returns the value from memory. And this is true even if the load instruction only takes one cycle from memory, which is already not incredibly realistic. Usually loads, depending on the cache behavior of the machine, how large the cache is, will take multiple cycles. And we'll see a pipeline that has multiple cycle loads a little bit later in the class. Good. So there do exist sequences of instructions that force us to stall. What did people do to get around this problem? They invented load delay slots, where in this particular, these early MIPS pipelines, because of the latency characteristics of a load, you'd actually have between 1 and 2 delay slots, depending on the pipeline, some number of delay slots. But what's interesting about these types of delay slots is that these types of delay slots, their semantics would be any instruction will go as long as it's independent of the load, as long as the load result is not required for that instruction. And interestingly, even though this idea also fell by the wayside for similar reasons as branch delay slots, an architectural style that we will learn about later in the course called VLIW came up with a very elegant way of imposing these independence constraints on instructions and used that to build a new type of ISA that resulted in a lot of ILP, instruction level parallelism, at very low hardware cost. The idea at a very high level, just to kind of whet your appetite now, is that in VLIW, instead of fetching one instruction at a time, you fetch a bundle of instructions at a time, where the fundamental object exposed to programmers is like this bundle and like what instructions you can like pack into the bundle. And the rule in VLIW is that you can pack different instructions inside of a bundle as long as they don't depend on one another. So you have these like little parallel units exposed to the ISA. And this turned out to be kind of very nice because depending on the way that you expose the bundle to the programmer, it's a lot more abstract than something like 1 or 2 delay slots, which is kind of very microarchitecture specific. But it's really doing a similar thing. Like the new semantic introduced to the ISA, this independence assumption, is the same. We will come back to VLIW. Very elegant idea, still used in DSP chips today. And of course, on the slide, I was saying, let's work with data hazards. Even if you fully bypass and you pull out all the tricks, your control hazards are still going to have bubbles. And something to keep in mind, especially as you go through your PSAT or are working on your midterm and are told to evaluate the trade-offs of different microarchitectures, when you have the iron law of performance, the processor performance equation, and you're using it to evaluate different design variants, like say one that exposes delay slots after branches versus one that does not, just bear in mind that despite the fact that a no-op is cheap and therefore decreases your average CPI, if you have not found any useful work to do in these delay slots, the number of instructions in your program is increasing. So just bear in mind that you can't cheat when you think about performance at the level of the processor performance equation, but you can cheat and be misled if you look at performance from the perspective of CPI. Just something to keep in mind. Okay, that is it for basic pipelining and the three major hazards: data, structural, and control. We're going to take a brief detour and talk about traps, interrupts, and exceptions, which is kind of an orthogonal topic, but will provide some context for later lectures. But before I go there, I just want to say that the pipelines that we start analyzing later in the lecture, so we've been talking about simple in-order pipelines, and eventually we're going to talk about out-of-order pipelines with speculation, with superscalar, all of these buzzwords. There's no new idea in terms of what we're trying to optimize when building those pipelines. So despite the buzzwords, all those buzzwords are trying to do is enable us to get as close to CPI equals 1 as possible. And you might be asking, well, that's a lot of buzzwords to just get to CPI equals 1, because we just went over a slide which said you're basically at CPI equals 1 if you do full bypassing and ignore control hazards, as long as you're not dealing with these pathological instruction sequences by like loads followed by arithmetic. So like, what's the big deal here? Like, what are these advanced pipelines actually bringing to the table? And the answer is that these slides have been a lie that has hidden what the CPI of a realistic machine actually is. So we say in these slides, oh yes, you can get like a CPI very close to 1 modulo these like corner case caveats. What we're neglecting to mention is how some arithmetic instructions like floating point ops take many cycles to complete, and your program may have a much higher CPI than the one reported here. We've only been dealing with the integer pipeline. And similarly, memory instructions don't return in one cycle, except in the rare case that we constantly pursue as memory system designers. Modern memory systems may take thousands of cycles to return the value of a load. You may miss in the TLB and have to do a page walk. You may miss in your so-called page walk caches, which are special hardware caches used to make the hardware page walks more efficient, and have to refill them. Finally, you get your page translation, potentially multiple full 2 DRAM latency accesses later, because page tables are a tree where you have to bounce from cache line to cache line, each of which may not be present in your caches, to get the translation at the leaves of the tree. Finally, you have your translation, you fill the TLB. Now you go to make your access to the data cache line that you're actually interested in, and it might itself miss in the cache hierarchy. Each 2 DRAM latency round trip on a modern architecture might be 100 plus clock cycles. So you're dealing with loads that could potentially take 1,000 or more cycles to resolve in the worst case. And so when you square that with the pipeline that we've been dealing with, these pipelines are completely ill-equipped for dealing with long latency operations like this, because everything is in order. If there's something in the memory stage that stalls, everything behind it just backs up, and we're not allowed to write back until the load actually returns, and your CPI could easily be proportional to the worst case memory latency on certain programs. So all of these buzzwords that we're going to be learning about later in the class, they are an attempt to get us back to CPI equals 1, despite the fact that some of our instructions, complex arithmetic and memory operations, take an extremely long period of time. That's what all of the fuss is about. But the concept, what we're optimizing, CPI, is fundamental and persistent across these later architectures. So just to keep in mind, everything boils down to CPI and correspondingly to the processor performance equation, or the iron law of performance. Okay, traps and interrupts. This is, like I said, a little bit orthogonal, but it will provide some context as we go through the class. So the deal with traps and interrupts and exceptions are, everything we've spoken about so far is programs in their so-called happy state. They're just executing instructions and they're writing and updating architectural state as they enter the write-back stage. What happens when you press a key? What happens when there's a divide by zero? What happens when you hit a page fault and are unable to translate the virtual to physical translation for a given memory access that you need? So for this, we need something out of band to invoke a handler to repair the situation or signal to the programmer that something has happened and that we should crash. So we're going to use the following terminology. This terminology is sadly not consistent across different textbooks, but this is the terminology that we will use. So an exception, we'll say, is an unusual internal event caused by a program during execution. So this is like arithmetic overflow, a page fault, something like that. An interrupt is an external event outside of the running program. So this is like if you press a key. It's not something that your program can anticipate, and it's not something that the program can blame on a particular instruction. So for example, if you have like a divide by zero, you point to the divide and you're like, yes, it's your fault. On the other hand, if it's something like a key press, it isn't really the fault of any particular instruction. A trap is how we deal with these types of events. A forced transfer of control to a supervisor to handle an exception or an interrupt. And it's just kind of noteworthy that not all exceptional behaviors result in traps. Some of them are kind of dealt with inline by the program because a trap bouncing back to supervisor is a rather expensive operation. So if you've seen early and for that matter modern pipelines that support floating point, there's often like a special register, and actually this is also true for integer pipelines today. There's a special register which encodes exceptional events and is accessible by the program. This is like an overflow bit after you perform an integer add, or a subnormal bit indicating that your floating point operation may not be high precision because of the input operand range. And then the program itself can just read that register directly and decide what it wants to do with it. But for all the other cases, we have this thing called a trap. So just a kind of brief history of exception handling. So this goes back to the analytical engine, which had overflow exceptions. So remember, the analytical engine was the 1800s era amazing machine that was 100 years ahead of its time. The first system, and this was exceptions that just like terminated the program. The first system that actually had traps was the UNIVAC 1 in 1951. And it did one of two things. It either had like a patch up routine. So if like an overflow happened, it would invoke a special several instruction handler to kind of patch things up. It would either do that and allow the program to resume, or it would just put a finger up in the wind and say, your program is now computing something incorrect. You should probably do something about it. Then we got a little bit more sophisticated with the DICE-SEAC, I believe it's pronounced. So this was a machine with two program counters where once you switched to the trap handler, you'd start rolling the second program counter. So we talked about micro PCs and ISA level PCs. Now we have yet another PC which walks through the interrupt handler or the trap handler whenever we bounce into an exception. Kind of a noteworthy machine in history. DICE-SEAC was the first so-called mobile computer. And by mobile, we don't exactly mean what we mean today. But hey, technically speaking, it rolled around. Its GPS coordinates changed over time. So asynchronous interrupts, like I said before, are these kind of extra program events that you can't anticipate. The way that we deal with them, and this is also the way that we deal with exceptions, is noteworthy. This is kind of like one of the clean ideas that came out of how is the ISA supposed to interoperate with an operating system when you've got to switch control into the operating system. So the idea is this notion of precise interrupts or precise exception handling. So basically the idea is as follows. If you have, who here has heard of precise exception handling, either from like an OS class or CS61C? Is the term familiar? One person. Okay. I think that's the lowest ratio we've had so far in this class. All right. If nobody's heard it, let's just briefly talk about the life of an OS designer if we didn't have precise exception handling. So if you have a machine that runs user programs underneath an operating system, and your microarchitecture is like a single cycle pipeline, like what you first learned about in 61C. If you have to spontaneously switch to the operating system to handle something like a system call or an interrupt or an exception, a thing of beauty about the single cycle pipeline is that it has no intermediate microarchitectural state. You just have architectural state come in the first set of input registers and architectural state updates right to the output registers of the pipeline. So you can, at a dime, just switch to the operating system, and if you return from the operating system and just load back the architectural state that was there at the moment that you moved into the operating system, then you'll be able to resume your program at the point that you left off, and no bad things happened, or no bad things would happen. If you switch to a more sophisticated pipeline, like one with multiple stages, like the 5-stage pipeline that we've been talking about in class so far, this gets a bit hairier, because now you have, at the moment that an exception occurs, all of the pipeline registers from fetch to write back are populated with instructions that are in the middle of their execution. So what do you do? Well, the hack that forced people to think a better way is you could just snapshot all of the microarchitectural state for whatever that pipeline was and kind of think about that blob of state as a part of the process state. So just like if you've taken an operating systems class, if you switch back to the operating system, you have a process control block which stores like the salient state that is needed to resume a process. You can just snapshot all of the register state for a given pipeline and kind of like think about it as a blob and lift it into the process control block. And then as soon as you're ready to resume, you just plop it back and populate every register exactly the way it was, and then hit the resume button, and you're off to the races. Can anyone quickly tell me why this is, or at least if you were the person designing the operating system to deal with this in a world with many microarchitectures, this is an extremely painful sounding idea? Yeah. Yeah, and for that matter, like this blob can like grow really large depending on how like deep the pipeline is. This is a not only deeply microarchitecture specific hack, you've got to kind of deal with this blob of state. You also need a way of lifting all the state out of the registers and plopping the state back on the registers, which means more wires out of the registers, not only the register file, but also the pipeline registers. And in general, this just makes life a disaster. And so people invented the concept of precise exception handling, which is this kind of like beautiful way of dealing with this problem, which absolutely has impact and is the way that we still design machines today, which is this abstraction which says, as complicated as your microarchitecture gets, when an exception occurs, or an interrupt occurs, but with an interrupt we'll have a degree of freedom in terms of which instruction in the program we want to associate with the interrupt. Let's stick with exceptions for a second. When an exception occurs, we're going to point our finger to the instruction that is responsible for the exception. This is like the divide by 0. You point your finger to the divide instruction. And you're going to allow the pipeline to drain and snapshot the architectural state in a way that is consistent with all instructions up to but not including the divide instruction having written back, and the PC that corresponds to the next instruction that we'll execute pointing to the divide. And no architectural state updates are made by instructions that are younger than the divide. So this is kind of like a way of getting back to the world of the single stage pipeline. We only have architectural state. We don't have microarchitectural state. The process control block only stores architectural program state, which is like the register file, the PC register, and the contents of data memory. And then when the operating system decides to resume, it just resumes by loading the architectural state back into the register file and data memory, and it loads the PC. The PC fetches the next instruction, which is divide, if you want to resume your execution, and then you go on. So this is the concept of precise exceptions. You point your finger to the instruction that caused the exception if it's an exception. If it's an interrupt, you have some wiggle room in terms of which instruction you want to associate with the exception. So the way it's often implemented is if someone presses a key or any other kind of interrupt event happens, there's a queue which feeds into the pipeline where the event gets buffered. And the pipeline can decide when something arrives at the queue when it wants to handle it. And for whenever it decides to handle the event, which should nominally be soon so that the latency of a key press isn't too big, then you associate a given instruction with the moment, the point of the precise interrupt handling, and then you follow that abstraction. You commit everything before and up to the instruction that is now associated with the interrupt, and then nothing else updates architectural state. You switch to your trap handler and you're done. Okay. So precise exception handling. With that in mind, we can view what the trap is doing in terms of like the interrupt handler, which is run on an exception or an interrupt, kind of like this. We have our instructions. We have an older instruction, and then once we've decided which instruction to point our finger to handle the interrupt or the exception, we're going to run this supervisor handler as if it were in line with the program at the point where the instruction that I'm pointing my finger to was in program order. So this is the abstraction that we get. So everything is still sequential, it's very clean, and it's just kind of like an interrupt handler that you just like kind of slip in there. A little bit, if you're doing operating system research and you're trying to implement a new type of operating system routine, a kind of nasty rat hole that you might fall into is for any handler that you add to the operating system, there's an opportunity for there to be a recursion or a nesting where you have an interrupt, you go from the program to the handler, another interrupt happens when you're in the middle of the handler, and so now you want to have a nesting of a second level of trap handling when you're already in the trap handler for the original instruction. And this can potentially go on forever. And for certain operations like demand paging where you're updating the page tables, if you're not very careful, it can result in the machine deadlocking. So there's a way that ISAs and operating systems, depending on the ISA, kind of deal with this problem. You want to be able to deal with nested traps and handlers unless you can guarantee that a given handler finishes very quickly, which is in general difficult to do because memory translation can unpredictably add overhead to these routines. The way that RISC-V does it is it has a second PC called the exception PC, EPC, and it will very early on in the trap handling process write that PC to the register file, which is kind of like pushing it on the stack. And when you push the PC and the state of the handler onto the stack or the register file, that's kind of like calling a function if you're just thinking about how normal programs execute. It allows if like another handler occurs in the middle of the one that you're currently servicing, you push it again onto the register file and you push it into like the stack memory and you just keep on going like that. And you can handle nested interrupts that way. This is just the way that RISC-V does it. And it has a special set of instructions for interrupting in and out of the trap handler, ERET, which is the way that you get back. Okay, synchronous traps, like I said, they occur due to a particular instruction. In general, they function the same way that I described with precise exception handling. And I just want to emphasize that, again, the precise exception handling tells us that all instructions up to but not including the instruction causing the exception will have completely finished their execution or their updates to architectural state. And this is so that we can resume the problematic instruction after deciding how to handle it in the hopes that we can repair its execution. Sometimes we can't, in which case the program crashes. Otherwise, we just go on. Okay. Last but not least, in terms of exception handling, how do we implement all of this without massively complicating our pipeline? We just spent the previous lecture talking about how we get different pieces of information, like when the branch condition is determined to be true, what the branch or the jump target is going to be at these different stages of the pipeline. And the more information that we have to be aware of, and the later it is in the pipeline, the harder our life generally is in terms of designing the pipeline to be efficient, minimizing bubbles, all of that. So what does that story look like with exception handling? Well, it looks pretty complicated. You've got a pipeline, and virtually every stage of a pipeline can result in problems that raise an exception. At the PC stage, you might jump to an illegal PC. That's an exception in the fetch stage. In the decode stage, you might grab an instruction that is not really an instruction because your PC, maybe like you, because this is all stored program computers, you wrote something bogus there. It's not a valid instruction. It decodes to garbage. That's an exception in the decode stage. Arithmetic stage, just like we were talking about before, arithmetic overflow, all sorts of problems can happen. In the memory stage, virtual translation failures, all sorts of bad things can happen. So what do? We invented this amazing way of thinking about exception handling in the pipeline. The idea is, well, we don't actually have to complicate our lives by taking super fast action in the cycle that we detect an exception. That's kind of analogous to, as soon as I know the branch condition, I want to immediately take action to prevent bubbles and this sort of thing. We don't need to do that here because there is a little bit of wiggle room in terms of when the exception is handled. Going back to precise exception handling, if I'm just responsible for putting my finger on like the divide instruction that has divided by 0, I don't need to do anything until the divide has reached the end of the pipeline. Because at the end of the day, all I have to give the OS is a consistent view of the program's architectural state up to but not including when the divide was about to execute. And so what we do to implement exception handling is for every stage that we can generate an exception, which is to say every stage period, we just kind of or whether an exception occurred with all of the previous stages indicating whether an exception occurred for that instruction. And we allow that exception status to kind of travel down the pipeline, kind of like the kill signals. And we resolve it all by the end of the pipeline when the instruction that is responsible for the problem is about to write back. And we just say, okay, we're going to stop. We're going to flip to our trap handler and we're going to continue that way. And when everything gets to the end, that's when we kind of broadcast our kill signals in the backwards direction, which is kind of similar to the way we did before. We just have a little bit more relaxed time in doing it because we can wait until the end of the pipeline. Okay, this picture, I saw this picture in 2009 for the first time in CS152, and I still find it kind of incredible that I wasn't practicing security at the time. I was just like a computer architecture undergraduate trying to learn about pipeline design. I soon started working on hardware security in around 2012, and it didn't occur to me, a regret, unfortunately, that I won't be able to get back, that this is probably the worst idea in the history of bad ideas from a hardware security perspective. And we'll have a few lectures that give you some technical depth as to why this is a really bad idea. But the way to kind of intuit why this is a bad idea is, has anybody written in their program like asserts, like assert that this is true, and if it's not true, crash your program. Everyone should be raising their hand. If you're not raising your hand, Google what an assert is and start writing your program with an assert. So an assert is kind of like an access check, kind of like a password check. So when you think about an assert and a password check, it's basically like if the person's password equals, like that they typed in equals the expected password, allow the subsequent code to execute, otherwise crash the program or go back to a screen which says you typed in your password incorrectly. So what this microarchitecture is essentially saying is when the instruction that determines that your password is correct or not figures that out, or when your assert figures out whether the condition is true or false, it's still going to execute a bunch of instructions in the shadow of that assert statement before it actually figures out and takes any action of the assert being false. And just to kind of make this more painful from a security perspective, remember, this is a very simple pipeline. Normally, loads take hundreds of cycles to resolve, which means that it's not 5 instructions which are going to be in flight behind an instruction that signals that we should be handling an exception. It's potentially hundreds of instructions across multiple functions that the user has written. So whenever you have at the software level a barrier which says do this check, and if anything wrong happens, go to the operating system, you're executing a huge swath of code after that, which is like counter to the whole point of having that assert there. When a programmer puts an assert there, they don't want anything executing after the assert. So this was exploited to enable an attacker to pretty trivially dump the contents of the operating system and many other address spaces that it should not have had access to. And when I say dump, I mean just walk through the operating system memory and dump the contents at like multiple kilobytes of bandwidth per second. And caused a great uproar in the hardware security community in 2018. We'll go over the mechanics of exactly how it works later in the course, but just suffice to say, I will look back on this slide fondly and forever think of missed opportunities. Okay. If you wanted to own a system, it was right there the whole time. Okay. Just to kind of finish off talking about exception handlings, this kind of notion of allowing things to bubble to the end of the pipeline and related to this security exploit that I just mentioned is related to a concept called speculation. This idea that we can kind of lazily handle the exception handling and only take action at the end of the pipeline is a way of implicitly speculating that an exception will not occur, which is a good bet to make. You want in microarchitecture to optimize for the common case. People don't press keys very quickly. So most of the time there will be no exception, there will be no divide by zero, so you can just kind of handle the exceptions slightly offset from when they're originally detected. Okay, that is trap handling. Any questions? Otherwise we'll go on to advanced pipelines. Yes? Yeah, very good point. The whole way that we're able to get around this security problem that I just alluded to is, well, the whole point of precise exception handling is, yeah, you can do a bunch of stuff in the shadow of the exception causing instruction, but it won't be architecturally visible because we're going to not do any of it. We're only going to write up to the instruction that is immediately older than the instruction causing the exception. So why does any of this matter? So it turns out that even if architectural state updates are not visible, microarchitectural state updates often are. And if you're clever and you can observe microarchitectural state updates that should never have happened because the instructions that caused them are in the shadow of one that might cause an exception, that's where the exploit occurs. And this goes all the way down the stack. Even if something is not microarchitecturally visible, it might be electrically visible all the way down to physics. So these types of abstractions that assume that updates at some level of the stack are not visible make a huge assumption from a security perspective when you consider lower levels of the stack. Good question. Any other questions? All right. Yeah, go for it.
Yeah.
Operating system detects it. It's not really the operating system's problem at that point. So the way to kind of think about it is let's walk through the lifetime of a key press just very quickly. So I press a key. When I press a key, I'm going to send a signal into like a first in, first out queue, like a FIFO queue, like a little hardware buffer that is the pipeline state knows when something has been written to it. And the pipeline will decide when it wants to pop off of that FIFO. And whenever it decides to pop, it's going to say, okay, I've just pulled this interrupt that I need to handle off of this FIFO. I'm going to allow all instructions in program order up to a specific instruction of my choosing to update architectural state. And at that point, when all of those architectural state updates are completed, it's going to flush the rest of the pipeline. That's what like that backwards signal was doing. And then only at that point is it going to put its finger in the air and signal to the operating system, hey, you need to do something, or the trap handler needs to do something. And here is this clean, consistent architectural state for this program, which created a trap, which consists of all of the architectural state updates in program order up to a particular instruction. Here is this architectural state. Please handle the trap for me. And then when you're ready to resume the program, you can just load the registers back into the architectural state registers and you're good to go. So the operating system actually doesn't see any of this. It just sees whenever the pipeline decided to resolve it, a clean, uniform, microarchitecture agnostic representation of the program, which is awesome for operating system designers. This is what they like. Any last questions? Okie dokie. Let me share this. That's good. Let me just make sure the slide share for our Zoom friends is consistent. Okay. And we have keyboard control, we do. Okay, by the way, when it says on the lecture slides, lecture 3, lecture 4, take the number to mean how many slide decks I've pushed to the calendar. Obviously, we're slipping a little bit, which is fine. We'll adjust the curriculum if I slip too far, but this is not lecture 3. So last time in lecture 3, iron law of performance, hazards, up to control hazards and the various different instructions, how we handle them, precise exceptions, interrupts, traps, and the worst security vulnerability ever discovered in processor design. We will not go through traps and all of this again. Hello again. Forever I will be plagued with that slide. Okay, so for the rest of today, we are going to up the ante and talk about more advanced pipelines. So far, we've had fun with a 5-stage pipeline. We've talked about how 5-stage pipeline design is actually quite hairy, and you have to be very careful to design your ISA to accommodate the different types of control flow instructions and data hazards so that on average, you're getting close to a CPI equals 1. We are gradually going to morph this pipeline into a more modern pipeline like what we will like what we see today in commercial machines. Our first step on this journey, or our first 2 steps, will be the same idea but dialed to 11, deeper pipelines, which is what this slide is about. And then later in this slide deck, we'll see the CDC 6600, which is a machine capable, well, it's got a ton of really cool features, but in the context of this, it's a machine that's capable of limited out-of-order execution to relieve some of the head-of-line blocking that might occur due to things like long latency loads or floating point operations. So that's where this slide deck will end. Okay, so to start, deeper pipelines. What's the idea here? Well, the idea is to accommodate larger instruction and data memories, which means that the time to access these memories will grow, but we have more ability to store instructions and data there, so our hit rates will be better. But to compensate for the fact that they are slower to access from an electrical perspective, we will pipeline them deeper. So this is the MIPS 4000 pipeline. It looks the same as far as the register file read and the execute stage are concerned, but the instruction memory stage and the data memory stage is deeper. So when you put an instruction or a PC into the instruction memory, you get out your instruction that you can store into the IR sometime later. And likewise for data memory, once you put an address in, you don't see what you're going to get until sometime later. Load to use delay. There's a very kind of nifty architectural feature in this design, which is that we'll talk about the pipeline from left to right. Starting on the left-hand side, the instruction cache was direct mapped. Now, why is this interesting? You all remember caching from 61C? So you have like a data memory, you've got a tag memory, you have to look up the tag in order to figure out whether the data that was read there corresponds to the actual thing that you wanted to get out, and the tag check has to be precise, sound and precise. So in this design, like any other cached architecture, when you look up instruction memory, so you're looking up a cache, you've got to grab the data from the data arrays, you've got to grab the tags from the tag arrays. This design didn't resolve the tag until after the data access. So it was a serial data tag lookup, but it didn't have to wait for the tag to come out to execute the instruction that it got out of the data array, which gets put into the IR register. It didn't have to wait until the tag came out to do some work, namely the RF stage for the instruction that comes out. And that had to do with a very clever combination of microarchitecture and the design of this machine, namely that its cache was direct mapped. Does anybody have an idea why it's okay for me to delay the tag check of an instruction until kind of midway through its execution if my cache that I'm getting the instruction out of is direct mapped? Another way of asking that is, would this idea work if my cache was set associative? Yes, exactly. So if you take the low order bits of your PC and use that to look up a set in the cache, recall back from 61C, you will read all of the data out at that set for each way in the cache. Each of those ways has an associated tag. You have to check all of those tags, and one of them at most will match the thing that you're interested in, and only at that point are you usually allowed to forward the data or use the result. If your cache, on the other hand, is direct mapped, then you at least have the guarantee that there's only one piece of data there. It may or may not have a correct tag. If it's an incorrect tag, then there was some other bogus instruction there, and you should definitely squash the thing that you read out and started computing on. But you don't have to worry about this problem of when I read the data out of a set, if it's a set associative cache, I'm getting multiple instructions out, and I don't know which one I actually need. So by being direct mapped, they have this nice property that they just get one thing out. They can execute that thing speculatively. If they find out that there's some tag mismatch, they'll just squash the pipeline. This is similar to a delayed exception from the previous slides and kind of feeds back to now you start to see, if you believe me, that the previous slide was the worst security vulnerability ever. We have a microarchitecture that is executing completely bogus instructions that may not even be valid instructions, and we're not even figuring out that it's executing bogus instructions until sometime later. So clever design allows them to speculatively execute an instruction and wait until later to do the tag check. Now, if the tag is always mismatching, then this machine is going to have bad performance because it's going to have to constantly squash these instructions after it's already done work for them. But the speculation here, or the design, is assuming that this in the common case will not be the case. Okay. Yeah.
Why
Yeah, that's a totally reasonable question. As far as I know, it was just a low-level consequence of the trade-offs in cache design. They wanted thinner caches, and even extending them by the amount of the tag memory in parallel was seen as too much. So they wanted very like thin buses, and as a result of that, did sequential accesses. And you could do it either tag first and then data, or data first and then tag. And they realized that if they had to live in one of those two worlds, we might as well do this new form of speculative execution. That's my best guess as to why they did it. I don't know 100%. Any other questions? Okay. All right, working our way down the pipeline. So now we have a cool way of getting instructions out, but we have a harder time dealing with various types of data and control hazards. So the data memory uses the same trick as the instruction memory. We have the tag check occurring later, which again, in this data first, tag second architecture allows us to get the data out earlier. And if there's a tag mismatch, we deal with it by squashing the pipeline. This enables us to forward data from a load instruction to dependent loads a little bit earlier. But even with that in mind, we still have the potential to have cycle bubbles. So when we were saying in the previous slide, load delay, like certain MIPS architectures have load delay slots, this is an example of an architecture that would motivate load delay slots. One where you're waiting a longer time in memory, therefore if the two independent instructions rely on the load, you'd have to wait. And so the load delay slot idea exposed a semantic which said put independent instructions in there and you can try to hide their cost. And this gives you a sense, again, why load delay slots died out. Because modern architectures are like this on steroids. Instead of like 3 cycles where I don't really care if the tag or the data comes out 1 cycle plus or minus ahead of time, you're dealing with loads that could potentially take hundreds of cycles. And you can't have a 100 delay slot machine. So suffice to say, loads were longer latency, and you could get around them using load delay slots. But you're now kind of like starting to see the rough edges on that idea. And same idea as before, direct mapped decache. This was great. You could get your data out a cycle earlier. You could speculate if your tag was mismatched, you'd flush the pipeline. Again, a kind of nifty form of speculation. Branches, similar thing. So we talked before about branch delay slots. Well, with this architecture, you need 3 branch delay slots in order to recoup the potential lost cycles just because of how deep the instruction memory access is. So this also begins to show you the rough edges on the delay slot idea. Again, 4 to 8 instructions per cycle on modern day machines, 25% are branches. Clearly, if we have to fill 3 delay slots per branch, well, that means by virtue of 25% of instructions being branches that every instruction is in the delay slot of a branch. And this idea, again, starts to show its wrinkles. Okay, so the takeaway for this pipeline is that we have to be a lot more careful when it comes to ensuring that useful work is being done in the shadow of these long latency operations, control instructions, load instructions, etc. So with that in mind, we're going to give several examples or walk through several examples for how code may have been written on a machine like this. So we're going to use this example. So this is a kind of simple vector-vector add in a loop. The term vector here just refers to the fact that A, B, and C are arrays. So we're doing a like operation at different offsets into this array. The term vector will come up again later in the course where we discuss vector architectures, which are architectures that are optimized for this type of code pattern where you're doing multiple parallel operations at different points in a space, like 3 arrays. So this is kind of like your standard vector-vector add in a loop. You walk through array B and C, you walk index by index, you write to a corresponding address A or offset from A. Everything is in parallel. and you're doing the same operation in each iteration. So if we translate that down to RISC-V code, we get something like this. We have floating point loads, which are, this is all in the context of this deep MIPS 4000 pipeline that we saw in the previous several slides. We have two floating point loads, we have a floating point add, we have a floating point store. We have this term bump pointer is just like the pointer increment and like bookkeeping logic. So we've got a bump through x2 or x1 rather, which is the offset into array A, x2, which is the offset into either B or C, and x3, which is the offset into the last remaining array. And then we take a branch, we go to the top, and we continue. So why will this have a higher CPI than ideally we'd probably like on the architecture that we just saw? What instructions are kind of killing us if I execute the code just like this? Any ideas? Remember, the iCache access is expensive and long, and the Vcache access is expensive. Yeah. Yeah, so these floating point loads, they take several cycles to come back, which means that especially for the second floating point load, the one that loads into F1, and then we immediately need to do the floating point add to produce F2, there's going to be multiple cycles of bubble in between these two, because it just takes too long to get out. This is going back to the instruction sequence that we said we didn't want to see earlier, load followed by a dependent arithmetic instruction. So it's like even worse on this microarchitecture because we've got these super long latency loads. So if I stuck you on a desert island and asked you to make this program faster on this microarchitecture, you can change the program, but you can't change the microarchitecture, what would you do? Anybody? Right, Ronan is one step. You're off the island. You're off the island, and you're off the island A because you got the answer right, and B because I don't want anyone else who's still stuck on the island getting the right answer from you. Anyone else who wants to wade into the shore or wade into the tide waters, what would you do? Say that again? Yeah, good idea. Very, very good idea. You take these instructions, so there's something very interesting about this code, and that is that you're kind of like, you're doing a bunch of math, which depends on loads, and then like a heavy floating point add, and then kind of separate from that, you're doing these bump pointers, these bump pointer operations. And the bump pointer operations are relatively cheap because they're just like integer operations, and they're only needed by the next iteration of loads because you've got to figure out where you're going to address lookup memory next, and the loop. So what you can do is you can move the bump pointers up before the floating point add to put some space in between the floating point add and the two loads. This is absolutely correct. You just take your bump pointer and you kind of scoot it up. So we haven't changed anything. This is the same set of instructions. We've just reordered the instructions. So this is what you do. Okay, now to Ronit's idea. If you want to do even better, there's a very cool trick. And the way that I'll put this is, suppose that the latency through your data memory was even worse. Suppose I gave you an infinite number of registers, and I told you that the latency into data memory was even worse than the MIPS R4000. Like say it's 10 cycles or something like that for argument's sake. Would you be able to move these instructions around and play this trick to hide the bubbles that result from the load and the dependent floating point add? Yes or no? Would you be able to if it was like 10 cycles long and you just were moving these instructions around? No, you wouldn't be able to, because we've really kind of exhausted this idea. We've moved the bump pointers up and we've gotten a few cycles of freedom that way. But if I dial the latency of these two floating point loads up, I'm eventually going to be in a position where the floating point add is just waiting for them to come back. And I can't move the floating point add at this point. all I can do is, because like, how else am I going to do it? Move it down one maybe, but that's basically it, because I need the store to go out after the floating point add, and I need the branch to come out afterwards. So we've exhausted this idea. So what we can do instead is a really cool idea called looping. So most people, I feel, they learn loop unrolling, and the way that they're taught it or the way that they think about it only exposes like 25% of why it's cool. So the first reason, or the first kind of idea behind loop unrolling, is to say, if you, let's say for argument's sake, know that you're going to execute the loop many times. And let's say that we know that it's going to execute an even number of iterations. So it's going to execute 2 iterations or 4 iterations or 8 iterations. Might not necessarily be true, and we have to deal with the case when it's not, but let's just for simplicity assume it's like 0, 2, 4, 8, something like this. What we can do is we can take the code for the loop body and we can copy paste it, and we can just execute 2 iterations back to back. And typically when people learn loop unrolling, they learn it in the context of you copy paste the loop, and the cool thing about copy pasting the loop is that you only have to do the bump pointer operations once for every super loop iteration, call it. So this code, don't stare at it too closely just yet, but just notice that the 2 bump pointer operations are incrementing by 16 now, whereas originally they were incrementing by 8. So by loop unrolling, we get fewer instructions per program because we can bump the pointers more. And the reason we were able to do that is that we can use the offset logic in RISC-V, namely 0 to x2, 0 to x3, 8 to x2, 8 to x3, to offset index into memory for a given bump pointer amount, which is no longer 8, which is now 16. But there's something very magical in addition to that, which has happened. And does anybody besides Ronit see what that is? Like, you look at this code looks kind of wild. Yeah. Bless you. Bless you, take a second. Mm-hmm.
So we kind of backward like time you but you can
Yeah, that's exactly right. So what this code is showing, everyone here knows what a matrix is? Even if you haven't taken linear algebra. I'm not asking you whether you've taken linear algebra, just what a matrix is. So like rows and columns. You can kind of think about the program that you're running for the purposes of this example. You can kind of think about the program you're running like a matrix, where a given row in the matrix is the instructions that you execute in a given loop iteration. And if you walk across the row, these are the instructions that you execute within that loop iteration. And then the next row down is just the instructions that you execute in the next loop iteration. And then you just go row by row, and you can kind of visualize your program like a matrix. What loop unrolling does is transpose this matrix. Now, instead of executing every instruction in a given loop iteration back to back, we're going to execute the first instruction of every loop iteration back to back. We're going to do both of the loads for the first iteration, or both the load for the first iteration. In here, I guess they haven't done the fully transpose, but nominally what you do is all the loads, all the floating point adds, all the stores, all the bump pointers, and then the branch. So we've taken our program, and by transposing it, we've maximized the amount of instructions in between any 2 instructions that are in what is logically the same loop iteration. So we do all the loads first. That means that we've maximally spaced out the time between the first load for the first iteration and the floating point add for what is logically the first iteration, so on and so forth down this loop. And what's magical about this is that this creates a beautiful schedule from the perspective of creating slack in how many instructions there are to deal with dependencies. And it's programmatic. I can actually take an arbitrary loop and I can transpose it like this. And if my pipeline doesn't need this level of kind of squeezing or stretching the instructions out, that's totally fine. It just means that I'm going to write back an instruction and then sometime later I'm actually going to use its result. But if I encounter a pipeline that does have these deeper latencies in like data memory or instruction memory, I'll, to the extent possible, given the amount of loop unrolling that I did, be able to hide that latency. Okay, loop unrolling. Does anybody see a problem with this? Yeah. Yeah. So there's a lot of, the kind of like basic problem here is an ISA has a limited number of labels and my code memory is precious and loop unrolling is exhausting both of these resources rapidly. I need many more registers to kind of deal with this technique and my program bloat kind of grows. But this is a beautiful, relatively automatic technique that people use to stretch out distances between dependent instructions to hide latencies on these types of machines. Okay, any questions on loop unrolling? Then we're going to do one more cool architecture and then call it a day. Yeah. It is, what would an optimizing compiler do today? So an optimizing compiler would probably not unroll to or beyond the number of GPRs, general purpose registers, that you have. So it would limit it by that. But I don't know if there's other heuristics that would kind of limit it further. Compilers today, especially auto-tuners, which are taking into account things like dynamic iCache, instruction cache miss rate as the program runs, might say if the instruction miss rate is higher than what it nominally be, it would actually just in time compile an unrolled loop to fewer iterations and might take into account kind of second order effects like that. But I think the only hard limit is just the number of GPRs, general purpose registers, that you have. Any other questions? Okay, one more cool architecture for today. So we're not quite at the CDC 6600, but this lays some interesting groundwork for it. So this is yet another way. So this is 252 only, but it's 3 minutes till the end of lecture. So if you're in 152, just sit tight and enjoy a really cool idea. So this is a style of architecture called decoupled. It's been kind of extended. So decoupled access execute is a really famous architectural paradigm, is kind of based on this like basic idea. And the idea is to notice that there's really two parts to this loop. Sorry, the colors are kind of awful because the slide to indicate 252 only is yellow. I apologize for that. The point is that the registers that are colored this like blue-green color are kind of the registers responsible for the data path of this loop, and the bump pointer and branch operations are the instructions responsible for just incrementing through the loop, and they don't have any impact on the actual arithmetic that is happening. And so the neat architectural idea, which is what decoupled is about, is by recognizing when a loop is really kind of logically two different loosely coupled parts and running them in a loosely coupled but in parallel fashion at their own rates, only signaling back and forth when needed in order to orchestrate control. So what this picture shows is there's kind of like two data paths here. So you imagine a microarchitecture that would implement this idea. It's really kind of like two data paths that are running at their own rates in parallel. And the first data path is the arithmetic or the integer data path, which is just calculating the bump pointer operations and the branches. So if you just strip out the loads and you strip out the floating point adds, imagine you're just generating these bump pointer increment values as quickly as you can and figuring out when you need to exit out of the loop. So you have one of these two decoupled processors just generating addresses as fast as they can. And then you have a second pipeline, which is receiving the addresses from the bump pointer pipeline queuing those operations up and executing them as quickly as it can. So the second pipeline is getting, you can think of them kind of as micro-ops. They're just addresses in an input queue which indicates where the vector loads need to go to next. But they just kind of buffer up like this. And as soon as there are addresses in the buffers, the vector loads occur at their own rate. As soon as the vector loads come back, the vector adds execute at their own rate. And as soon as the vector adds come back, the vector stores execute at their own rate. And what's kind of beautiful about this is you can think of the two different pipelines running in parallel. So all of the overhead of the loop, bump, pointer, branch instructions is gone. And the pipeline control of the kind of heavyweight floating point arithmetic part, the one that's actually doing the floating point math, is operating within a simpler pipeline as fast as it will go, and any hazard that might have come up because of bump pointer or branch orchestration or anything like that is just out of the picture. All it's executing is if there are addresses at the input queues, grab them, do the loads, return the load value, execute the floating point add, do the store, done. It's kind of like a much simpler data path. And so what you end up getting is kind of like a different control paradigm where you have like an efficient integer unit which is responsible for control, and it has to be very careful about control hazards and data hazards, orchestrating like when the loop needs to terminate and all of that. But all the math that it does is super simple, so we can kind of like orchestrate that in like a 5-stage pipeline. And then the heavier math, which might take more cycles to complete per op because maybe floating point add takes multiple cycles, is in a separate pipeline where those latencies of longer operations from the floating point loads or the floating point adds are kind of naturally tolerated because the whole thing is just doing a feed forward operation with none of these nasty control hazard back edges and interleaved arithmetic operations responsible for bump pointers. So it's just kind of a way of recognizing complicated but simple integer control, less complicated feed forward but more computationally expensive logic, splitting those apart and running them in parallel. And with that, we'll end lecture for today. I'll see you all on Thursday. Cheers, Zoomers.
I have a I see that we have already assigned the reading here, and I'm wondering what is the deadline for these project?
It's going to be, oh, say the very last thing again?
What is our deadline to